So welcome to the second lecture in statistical problems and simulation. This lecture will be about generating random numbers. I who will be presenting this is Jens Zander. I'm a professor in radio communication systems at the Department of Communication Systems at the School of ICT at KTH in Stockholm. The topic of today's lecture is random numbers. In our simulation experiments, we require sequences of usually independent random numbers x1, x2, up to xn. And there are a number of philosophical questions that arise. What is a random number? And how do we know that a sequence of numbers that we generate is actually random? And does it actually matter? And how can we generate a random number in a deterministic computer? These are issues we're going to start with dealing with in this lecture. So looking at this first question, what is a random number or a sequence of random numbers? Well, this is a quite philosophical question, and if you look at the everyday notion, it will probably be something that is unpredictable, a number that's generated that is unpredictable. You cannot predict this from previously generated numbers. This everyday notion, however, is somewhat vague, and there have been, of course, a number of attempts in history to make this definition a little bit more precise. One of them is, of the researchers that have been doing this, is Claude Shannon, and he discusses randomness in terms of information content. If you have a sequence of bits, for instance, then a random bit is something that has maximum information content, and the information content then is 1 bit per bit. Whereas a completely predictable bit that you would get out of that you can completely predict from the previous bits will have information content 0. On a very similar notion, Kolmogorov discussed the complexity of sequences. If you have a sequence of numbers and the randomness is related to the complexity that would be required in terms of an algorithm that would generate the next number in that sequence. And perfectly random numbers would, of course, require basically infinite complexity, or the only way to describe the next number would actually to give the next number. So the algorithm would just contain a table with the numbers. Both Shannon and Kolmogorov's definition have the property that if you have an infinite sequence, the information content of a purely random sequence will be infinite, or the complexity in the Kolmogorov case will be infinite, since we simply have to give the sequence itself. There's no way of computing it in a more effective way. Of course, in practice, this is a technical problem, and in practice we actually take a sequence of numbers as random if it can pass a number of statistical tests, if it has the right distribution, if it has the correlation property that we want, or other statistical properties. The latter is, of course, important when we actually want to generate random numbers in the computer. And basically there are two types of ways of generating random numbers. One is to use a true random generator, which is typically a physical device that picks up atmospheric or thermal noise and generates a number. There are actually on the web random number servers, for instance, www.random.org, that provides random numbers generated in this way. And they can be seen as truly random, because it's of course, very difficult to predict the random movements of particles in a resistor or in the atmospheric gases. In practice, however, we are confined to pseudo-random generators. And these are algorithms that generate random numbers or pseudo-random numbers in the digital computers. And of course, since they are generated in a random, since they're generated in a computer, they cannot be truly random, but they are in fact long sequences of numbers that fulfill a number of statistical tests. And this And this brings us to the definition of a pseudo-random number or a pseudo-random generator. A sequence of pseudo-random numbers is a deterministic sequence of numbers having the same statistical properties as a corresponding sequence of truly random numbers. And throughout history, there have been a number of attempts to generate such numbers. One example from the 50s is the congruential generators. And there have been attempts even earlier in the advent of digital computers. Von Neumann's famous middle square method from 1940 is probably the forerunner. But congruential generators from the 50s by Lehmann works basically this way, that you take a seed or a number that you start the algorithm with, and then you multiply it with a large number, and then you take the result modulo m. And the latter one is of course to confine the result to the size of maximum m. And this of course operates on integers, and in order to get a uniform distributed value between 0 and 1, which is the common random generator in most software packages, you have to divide by m. There's also a variation called the mixed congruential generator. Then you add a constant. This is to avoid, if you add up with a seed of 0, then the first version doesn't work. It only returns 0 all the time. The mixed congruential generator avoids this. Both the mixed and the congruential generators, as I said, operate on integer arithmetic. Another very popular way of generating pseudo-random numbers is to use linear feedback shift registers, and they look basically like this. They have a shift register that is fed back, and so the content of the shift register is shifted to the left, and then the output is then calculated through a network of ands and ors. And let's look at some of the properties of pseudo-random generators. All pseudo-random generators are calculated in a computer or in hardware, and they are digital state machines. So they have a number of states that they can run through. For instance, in the congruential generator, since the maximum number is m and we take the result modulo m, there are in total m states. In the linear feedback shift register with k memory cells, there will be 2 to the k different states. And as we know from digital design, the machine will run through these states, and it can do it in various ways. It can run in cycles of this type. It can run in several loops, and it can have a transient state that will stay for a while and then enters a stationary state, and there will be a number of loops in these random generators. And what is of course important for a random generator is factors like the cycle length. How many numbers do we generate until it repeats itself? And the question is, are there transient states? Do we have to run the pseudo-random generator for a while first before it enters one of these long, preferably long loops? And what is dependence on the seed or the initial state that we start in? If we unlucky, we can start in a cycle that is very short, so like on the right hand side, and most of the design of pseudo-random generators has been focused on how to get the maximum length of generators. And for instance, in the congruential or mixed congruential generators, how should we choose these parameters A and C in order to get a loop configuration that looks like on the right-hand side, or in the linear feedback shift register, we would like to get the feedback components such that we can reach the maximum length of the of the state loop, so that we will get something like on the right hand side. And this is an example of a maximum length loop, state loop for a pseudo-random generator. This is for a standard congruential generator where there will always be a single state. The zero state will always feed back to itself. But then if we have a maximum length pseudo-random generator, we can get a full loop like on the left hand side. So how do these generators perform? Let's have a look at a few examples and what can go wrong if we pick the A's and the C's in the wrong way, and what does it look like. In these two graphs I have plotted pairs of numbers, x1 plus 1, the two subsequent numbers in the cycle that's generated by these generators. In the left-hand side, I've plotted the generator used in Microsoft Excel, and as you can see, there's no particular pattern. It looks very random. These are 2048 different numbers, and on the right-hand side, however, I have a mixed congruential generators with A 157, C equal to 1, with M equal to 2048, and of course the numbers run through all the possible combinations of ones and zeros, but you can clearly see that two subsequent numbers have a very distinct relationship, as is shown in the vertical bands, or sorry, in the diagonal bands. So this little animation shows a maximum feedback shift register example. This is a 4-stage register, and this is the maximum length sequence. And the output generated you can see below here. And since it's a maximum length register, it will run through all the 15 states, 2 to the 4 minus 1 states. And if we avoid to feed it with a 0 to start with, it will run through all these states. And it has some very nice combinatorial properties. For instance, every 4 tuple of numbers, binary numbers, will appear in the output sequence, since the output sequence is simply the image of the register content that will be run through exactly once. This also means that the numbers of ones and zeros will be almost equal. There will be 8 ones and 7 zeros. And if you look at longer shift register, then the difference between ones and zero, number of ones and zeros, will be neglectable. So this is a sequence that has sort of perfect properties. It's almost perfect to be random, of course, but it has all the statistical properties that is needed for a random generator, even though it is very simple to predict the next output. So how do we validate a random number generator? And give you two examples there of rolls of a pseudo-random dice. And the question is are these sequences random? They contain the same number of ones and twos and threes, whereas the first one has a sort of a random look, whereas the second sequence 1, 2, 3, 4, 5, 6 is just in order. But are these, in a statistical sense, random? To determine this, we have to expose them to a number of statistical tests. And the statistical tests will test the distribution, the probability, and the autocorrelation properties. And we will get back to those validation techniques in more detail in lecture 5. Okay, so now I'm gonna need a random number generator, and my standard software package that I'm using in MATLAB or in Excel or in Java provides me with a random function, RND, as a function of a seed. And can I use this without any problems? Well, the typical random number generator in a software package provides you with a uniform floating point, uniform or rectangular variable equal distributed over the intervals 0 to 1. And I would say that the randomness or the fulfillment of statistical properties is sufficient for most purposes in the standard packages. They have the nice advantages by feeding them with the same seed. They can generate exactly the same sequence, so it can be good for comparison if you want to compare different systems, as we saw in the previous lecture. Caution should only be exercised when you're dealing with extreme situations, when you're interested in the tails of the distributions. We gave an example previously. If you're really interested in the tails of the normal distribution, when you want to make experiments with very rare events, then it could be a good idea to check your random generator for the statistical properties that are important for that particular experiment. So that leads us to the first quiz about random number generation, and as usually there are 4 statements, and you can pause here to consider your answers, and when you're done, continue with the video. And that brings us to the answers. Correct answers are B. A congruential generator can never have a cycle length larger than m, the modulus. The linear feedback shift registers are suitable for implementation in software if the register length is equal to the word length of the computer. Yes, otherwise these operations becomes very tedious to do. The next random number from a pseudorandom generator can always be predicted. Yes, that is the property, and we saw this typically in the linear feedback shift register and the congruential generators. So let's continue now with random numbers for a given distribution, arbitrary distribution. We have so far generated uniform random variables, so we have a continuous random variable u with rectangular or uniform distribution over the interval 0, 1. And the question is now, how do we generate discrete random variables x with a given probability distribution, and how do we generate continuous random variables x with a given cumulative probability distribution function or a probability density function. And this is the problem that we're going to discuss now. So let's start with discrete random variables. In the following, we'll see that basically 3 methods will reoccur, both for discrete and continuous variables, and these methods are slight variations of each other. The first method that we will consider is the inverse transform method, or for discrete variables also called the table method, since it's based on a table of the cumulative distribution of the variable that we want to generate. So the table on the right-hand side contains the cumulative probabilities, and that is the probabilities that x is less than xj in row j. And we generate a uniform random variable, and then we compare the uniform random variable with the entries in the table, and when we find a table entry that is larger than u, then we output the corresponding index or the value of that row of the table. To illustrate this, we use a simple quiz or a problem, and we ask you to use this inverse transform table method to simulate a fair die. And as usually, write down a simple pseudocode and give us the table contents. Stop the recording here. Use a pen and a piece of paper before going through the possible solutions on the next slide. And here is the answer, possible answer. On the right hand side you have the cumulative probability table, contains 1, 6, 2, 6 and all the way up to 1, since the individual probabilities of the outcomes is 1/6 each. And the pseudocode is that you generate U, and then you go through the table step by step until you find the value that where U exceeds the table entry, and then you output the corresponding index. The next method we're going to look at is the acceptance rejection method, or simply the rejection method. In this case, we assume that we have access to a random variable y with some distribution qj. That is very similar to the probability distribution of x, the random variable that you want to generate. We assume that this variable has the distribution pj. And how do we do it? We pick a constant c that is has the property that at all times the ratio between pj and qj for all j should be less or equal than c. And then we use the simple procedure that we first generate y, and we also generate a uniform random variable. And if u is less than the ratio of p and c times q, then we output x as equal to y. Otherwise, we repeat the process, and so we keep on until we have what we call an acceptance, when x is accepted as y. The question is, how long will this process take? Well, the number of generations or iterations of this process until we get acceptance is a geometrically distributed variable with average c. So on the average, it will take c steps, where every step has the probability of acceptance 1 over c. So you can see that if c needs to be chosen very large, and this means if p and q differ a lot, then this is not a very good method, since we will be having to repeat the process very many times. It's not a very efficient method. So this works well if c can be kept moderately small, and also which means that p and q are reasonably similar distributions. The third method is the composition method, and it's quite simple. Assume that we have two random variables x1 and x2, each with their distributions, and we generate a variable x simply by, with a certain probability alpha, picking x1, and with the probability 1 minus alpha, picking the other one. And of course, assuming that alpha is between 0 and 1. And this is a way how to instrument the random pick by using a uniform random variable. We can show that the output distribution x is simply the weighted sum of the input distributions. And it's clear to see that this method can be generalized to an arbitrary number of variables. So it will be, the output will be the weighted sum of these variables. Just make sure that the sum of the components alpha I sum up to 1. And this is a good method to when it's obvious that the distributions can be composed as weighted sums. So let's finally move on to continuous random variables. And let's start again with the inverse transform method. And the inverse transform method now becomes obvious why it has its name. Assume that we again have a uniform random variable, and we want to design a output variable x with a given distribution. And the trick we want to use is that we want to apply a function g on the uniform variable u, and that should give us x. So the question is now, how should we choose g such that x gets the wanted distribution? Let's look at the distribution of x. This is the distribution function. Definition of distribution functions, that's the probability that x is smaller or equal than small x. And if we plug in that x is equal to g of u, we get the next step. And if we suppose that g is a monotonously increasing function, which means that its inverse exists, we can solve for u, and we get the relationship like this. And we recognize that this is the definition of the distribution function of u in the point g minus 1 of x. And since the distribution function of a uniform variable is simply x, we can see that the distribution function of x of x will now simply be g minus 1 of x. So this gives us an idea on how we should pick the pick g. So our method will be that we generate a uniform random variable, and then we subject that to the function fx minus 1, to the inverse of the distribution function of x, and that will give us a random variable x that has the required distribution function fx of x. To give you an example, simple example is a very common example, and that's the exponential distribution that we'll use many times in the course. The exponential distribution has a density function that looks like this, 1 over lambda times e to the minus lambda x. And if we integrate this, we get the cumulative distribution function, 1 minus e to the minus lambda x. And if we compute the inverse, it will look like this, minus 1 over lambda, the natural logarithm 1 minus of 1 minus u. So the method now is clear. We generate u. We put u through the inverse of the distribution function of x, and this will give us 1 minus 1 over lambda ln 1 minus u. And we recognize finally that 1 minus u also is a rectangular distributed variable. Mirror imaging around 1/2 doesn't change the statistical properties of u. So we simply get minus 1 over lambda ln u as the output generator. And that brings us to quiz number 3, which is an application of the previous. We're going to compute a Poisson distributed variable n using the exponential distribution in the previous slide. The property that we'll use is the property of a Poisson process, as illustrated in the graph here. We have a timeline here, and we have stars marking the time events of Poisson events. And we know from the Poisson process properties that the inter-arrival times of these events are independent exponential distributed variables, x1, x2, x3, and so on. We also know that the number of events in a time interval 0, 1, a unit time interval of a Poisson process with intensity lambda is Poisson distributed with intensity lambda. So, so what we need to do is to generate exponentially distributed inter-arrival times until they sum up to 1, and count how many of these inter-arrival times we need to sum up before we reach 1, and that number will be a Poisson distributed variable. So again pause the video here, use a pen and a piece of paper to describe the solution and give us the pseudocode of your simulation. So this is what it will look like. The idea is simply that you generate exponential distributed variables and sum them up until the sum exceeds 1. And the number of such variables that you add before you reach 1 is simply the Poisson distributed number. And that is, of course, a discrete random variable n in our case. And that brings us to the acceptance rejection method or rejection method in its continuous version, which is the second cookbook recipe. And again, we assume that we have an efficient way of generating a random variable y with a certain density gy. And we want to generate x with a similar distribution fx. And of course, again, we pick a c that is such that the ratio between the functions f and g is less than c for all y. And the procedure is exactly the same. We generate a y with a certain with the probability g, distribution g, and then we generate a uniform variable, and then we make this comparison of the ratio between f and g. And if the ratio is larger than the uniform random variable, then we pick x as y, otherwise we repeat. And again, the number of iterations is on the average is c. It's a geometrically distributed variable. And if the functions f and g are not very similar, then c has to be picked large, and that means that the distribution differ a lot, and then this process will take a long time. So this method works when f and g are reasonably similar. And finally, the composition method in the continuous version, it's exactly the same. We have, again, two random variables, x1 and x2, with the densities f1 and f2. And we pick one of the component random variables with probability alpha and the other one with 1 minus alpha. And the distribution, again, is now the weighted sum, not of the probabilities, but it's the weighted sum of the densities. And again, we can generalize this to arbitrary number of variables. And this is a good way if we can see that the wanted density fx can be composed out of component densities in this way. And finally, let's wrap this up with a very, very common distribution that will be found in many simulations, and that is the normal or Gaussian distributed variable. And there are many ways of doing this. And of course, the obvious cookbook method is to use the inverse transform method. And so what you would do is that you would subject a uniform variable to the inverse of the Gaussian distribution function cap phi minus 1. The technical problem is there is no closed form expression for this function, so it's only tabulated, and there are a number of numerical approximations. And the numerical approximations usually work close to the average, but tend to be not so good in the tails of the distribution. So if you're interested in the tails of the distribution, this may not be the optimum method. But this is very commonly used in many of the random generators that actually provide normal random variables in software packages around. The other one is, of course, the central limit theory. We know that the sum of arbitrary identically distributed random variables they converge towards, or asymptotically converge to a normal or Gaussian distribution. So for instance, if we sum up uniform random variables, n of them, this will approach like this will approach a normal or a Gaussian distribution. The question is, how many of these variables should we add in order to get the appropriate accuracy? First of all, you can see that if you add n components, n 0, 1 rectangular distributed components, the values can never exceed n over 2 or minus, go outside the range n over 2 and minus n over 2. So if you're interested in tails that are longer than that, then this may not be a good method, or you have to increase the number of components that you sum. The most popular method that gets around these problems is what they call the polar or the Box-Muller transform method. And it's based on the observation that if you have x and y, a pair of independent normally distributed variables, then if you see them as a point in space, and you use the polar description of this point in the plane, you can describe it with a distance r and angle phi, and we know that the distance r squared is simply to Pythagoras' theorem. It's x squared plus y squared, and if x and y are normal distributed variable, this will be an exponentially distributed variable with intensity 1 over 2. It will have twice the power, or twice the variance of the individual components, or the variance will be 2. And the angle phi, which is the arctangent x y over x, and that will be a uniformly distributed variable over 0 to 2 pi. And this property we can use in a method to generate a pair of uniform random variables. Instead of going for the normal variables directly, we instead generate r and phi. And r is an exponential distributed variable. We use the inverse transform method, which we now have an exact answer for, and that will be minus 2 lambda u, and then we take the square root of that to get r. And phi is simply a uniform distributed variable, so that will be 2 pi times u. That will now be a uniform variable over 0 to 2 pi. And if we compute one variable x as the r times the cosine of phi, and y as the sine of phi, we get two not independent but uncorrelated variables x and y that will test positively against all the tests that you can do for normal random variables. So this is a very effective method that gives you the exact distribution. So let's wrap this up with a quiz on continuous random variables. As usual, pause here and figure out the answers, and I'll be right back with the correct answers. And here are the answers. The correct answer is A. In low error probability link simulations, you're interested in very rare events, low error probabilities. Then you're interested in the tails of the Gaussian distribution, and the inverse transform method based on numerical approximations, which are usually good around the average or the origin. They may not work very well on the tails, so you have to be careful there. The polar methods are used to generate Gaussian variables. The rejection method works fine for continuous variables, and the resulting cumulative distribution function is not the weighted sum of the cumulative distributions, actually the densities, that is the weighted sum of the densities of the component variables. So this completes lecture number 2.